So we all know about some mathematical constants, right? Numbers that don't change no matter what. Like 1, 2, 0, -1. Wait a minute. I'm making it look like you guys are gonna know everything about this presentation already. And I can't do that. But fortunately, I know why you came here. I don't know who this guy is though. So today, I'm gonna... So this is a circle. So pi, if we make that into radians, that'll get us around 1/2 of a circle, which is 180 degrees. And tau, if we make that radians, we'll go around a whole circle, which is 360 degrees. So yeah, tau is basically just 2 pi. Up next are the square roots. Get it? Okay, but in reality, triangles with angles and sides and all that new gen sorcery will have these square roots as part of the ratios for the lengths of their sides. For the square root of 2, its length is the hypotenuse, while for the square root of 3, its length is the side opposite the 60-degree angle. But this plane I just drew here is the square root of 5. Why? Well, I'm glad you asked. Why is this guy bad? This is the golden ratio. And this is regular pentagon. Okay, yeah, this is boring. See that phi symbol right there? Yeah, it's actually completely pointless. Get it out of here. We need something better. Something less arbitrary. Okay, that's pretty convenient. So yeah, this is just a pentagon's diagonal divided by its side length. It's not too hard once you get to know it. Next, we have the silver ratio. It's, this. Yeah. Is there a bronze ratio, some of you might ask? No, there isn't, but what there is a super golden ratio. So let's quickly check out the value of that one. Yeah, I'm not going over that. At least the one use case I could find for this is actually pretty cool. But what if we use the golden ratio to divide a circle's circumference or something? Well, I did that for you. Also, this arc is roughly 137.5 degrees. You might need it, I don't know. Finally, we have the Dottie number. Actually, that's misleading. This uses cosine. That has nothing to do with dots. Hang on, do we even need the because this is just cosine of x equals x. Anyone could calculate this one, even without triangles. Okay, so the first number here, oh, hang on a sec. Okay, so the first number here is Euler's number. It's the base in the natural logarithm. Basically, e to the power of whatever number gets you x. But this is pretty easy. So next up, we have Wallace's constant. Hey, wait a second. Grr. Moving on, we just have numbers that aren't easier to explain with shapes. At least for the audience, this will probably reach. We have 2 to the power of the square root of 2, the natural logarithm of 2. Hey, maybe I should evaluate some of these. This is getting pretty repetitive. Next, we have the Euler-Mascheroni constant. It's not Euler's number, nor is it the lowercase y, but what it is the limiting difference between the harmonic series and that natural logarithm I was talking about. What do I mean by this? Well, we can use a graph for this one. As we approach infinity on the x-axis, the blue area will eventually converge to the value of the Euler-Mascheroni constant. Okay, this one's just the sum of the reciprocals of every Mersenne prime. What's a Mersenne prime? Let's just make sure p here is a prime number for every term in the sequence, and you're good to go. Here's some more sigma notation while I'm here, because I said so. This one's a Paris constant, and it produces the sum of the reciprocals of every cube number. This one, that's Liouville's constant, and it produces the sum of the reciprocals of 10 to the power of every factorial number. And this one, that's Catalan's constant. It controls both the sign and the number. Maybe I should go before I get addicted to this. This is what we start with? I mean, it can't be that bad, alright? Hold on a second. I'm not that dumb. I know what type of alphanumeric memes this generation laughs at nowadays, and it's definitely not E. So here's a formula that steals from the E formula we saw earlier by removing one thing. It's plagiarism, but modern. Next, we have the plastic ratio. At least they'll get a break from these unhinged constants, bro. Here's some polynomials. Maybe I should solve them to get my mind off of that. What do you mean no one solved this equation yet? Whatever. Anyways, okay, this one isn't even a number. Okay. Finally, something I can explain. This is not 120 factorial. That would be too big. Instead, double factorials multiply the number with every other number below it. So this is 5 times 3 times 1, or 15. Anyways, on to more number. Okay, this dude is back. Get him out of here. Okay, someone legitimately just got bored while typing this. So here's an obligatory metal pipe. But this is actually part of a very mildly interesting formula. Just pick any natural number. Okay. Then put it into a multiplication table of that size and count every distinct integer. 14 of them. The number that determines what you get from this actually uses that constant. Speaking of the next constant, that's the square ice constant. And here's what it's used in. As for the little O notation, don't worry about it. This is just how many Eulerian orientations we can have of an n by n periodic grid graph. And by Eulerian orientation, that means every circle here has the same number of arrows going in and going out. Here's the look and stay sequence, which will help determine our next constant. If we take 1, we can read that as 1, 1. If you make that into a number, that's 1, 1. Now read it again, 2 1s. Then it's 2, 1. Now read this one. That's 1, 2, 1, 1. 1, 2, 1, 1. Read that, you get 1, 1, 1, 2, 2 1s. 1, 1, 1, 2, 2, 1. And then 3 1s, 2 2s, 1, 1, etc. But this sequence is actually kind of pointless, unless we can figure out the average growth rate of it, because that's what we're after here. So do we figure it out? Yes. Here's the very sophisticated research team that did it. Alright, there's only one more constant left. I better have some mercy here, otherwise I'm gonna lose my mind over this. So what did you learn today? Because I learned how to overdose on mathematics. Alright, bye.
What's up, guys? It's Quandale Dingle here. Or starts now.